Hello, my name is Giacomo and today I'm excited to present you our work on evaluation techniques and neural architectures for compositional generalization. This work was carried out at IBM Research in collaboration with ETH Zurich. In this study, we evaluated compositional generalization in vision models. Compositional generalization is the ability to generalize at inference time to unknown combinations of known generative factors, such as color or shape. We first started by observing that previous works evaluated compositional generalization under significantly heterogeneous assumption, making comparability hard. Consider this example, where images are generated according to three main factors, which are color, size, and shape. Some works evaluated generalization by excluding only one combination, resulting in a similarity between generative factors of test and training examples equal to 2. On the other hand, others considered the stricter condition where some test samples only overlapped on a single attribute with training samples, making the problem significantly more challenging. To solve the issue, we proposed a unified evaluation framework called orthotopic evaluation that allows for a more rigorous compositional evaluation by exposing semantic similarity as an hyperparameter of the framework itself. Experimentally, we find that this parameter significantly affects the observed generalization. Theoretically, this phenomenon can be framed as a ladder of compositional difficulty, spanning all the spectrum from in-distribution evaluation to extrapolation to unseen attribute values. This observation is held on a wide range of datasets and models. Furthermore, orthotopic evaluation creates evaluation splits based on a procedure that iteratively projects and prunes the original dataset. This allows to increase the efficiency of the evaluation, reducing its complexity compared to previous arts from exponential to constant in the number of generative factors. Leveraging orthotopic evaluation, we provide an up-to-date picture of the compositional generalization capabilities of state-of-the-art vision models. The results highlight that modern vision architectures still struggle on this task, suggesting that they don't incorporate enough bias towards compositionality in their representations. Also, we observe two interesting phenomena. Firstly, monolithic networks are parameter efficient, as the model shares a single set of weights across attributes, and different attributes are read out from the same compressed representation. However, they fail at generalizing compositionally. On the other hand, architectures that disentangle their weights across different attributes generalize well compositionally, but are very parameter inefficient. Inspired by these, we propose attribute invariant networks, an architectural blueprint that disentangles only the first layer of the network while sharing the rest of the weights across the attributes. Attribute invariant networks combine the best of both worlds, being almost as parameter efficient as monolithic networks and generalizing almost as well as fully disentangled networks. Experimentally, we show that attribute invariant networks achieve Pareto optimality in the trade-off between generalization and number of parameters. Summing up, in this paper we made two main contributions. Firstly, we proposed the orthotopic evaluation framework, which made measuring compositional generalization faster and more rigorous. Secondly, we proposed attribute invariant networks, which achieved Pareto optimality on the compositional generalization task. That concludes my presentation. If you are interested in our work, please check out our paper and open source code implementation. Thank you for watching and see you at NeurIPS.